Electromagnetic induction was discovered independently by Michael Faraday in 1831 and Joseph Henry in 1832. But Faraday was the first to publish the results of his experiments. In 1834, German physicist Heinrich Friedrich Lenz, 1804 to 1865, deduced a rule known as Lenz's Law, which gives the polarity of the induced EMF in a clear and concise fashion. Let's learn about Lenz's work in this session. Before we start explaining Lenz's law, let's perform a simple activity. Take a copper tube, which is conductive but non-magnetic. Drop a piece of steel down through the tube. It falls rapidly under the pull of gravity. Now, through the same copper tube, drop a magnet. You will notice that the magnet falls very slowly. Why does this happen? This phenomenon can be explained by Lenz's law. When the north pole of a bar magnet approaches a coil, magnetic field lines and hence the magnetic flux linked to the coil changes. This gives rise to an electromotive force according to Faraday's law of electromagnetic induction. This induced EMF, in turn, generates a current in the coil, and it flows in the anti-clockwise direction. Here, the movement of dots indicates the flow of conventional current. This induced current, in turn, generates its own magnetic field in such a way that the face of the coil facing the north pole of the bar magnet acts as a north pole of the induced magnetic field. Since like poles repel each other, the secondary magnetic field tends to oppose the motion of the approaching bar magnet. The mechanical energy spent in overcoming this repulsive force is converted into electrical energy. Similarly, when a magnet moves away from the coil, the induced current flows clockwise, making the end of the coil facing the magnet as a south pole. Therefore, the north pole of the magnet has to overcome the attractive force between the south pole of the induced magnetic field and the north pole of the bar magnet. Again, the mechanical energy spent in overcoming the force of attraction is converted into electrical energy. So, we have seen the direction of current and the magnetic field for the to and fro motion of the bar magnet. From this, we can see that an induced EMF generates a current in such a direction that the induced secondary magnetic field opposes the magnetic field inducing the current. This is known as Lenz's law. To verify the above statement, imagine for a moment that the north pole of a magnet approaching the coil induces a current in the coil in the clockwise direction. As a result, the end of the coil facing the magnet becomes the south pole. Then, due to inherent attraction between the unlike poles, the magnet would be automatically pulled towards the coil without the expenditure of any mechanical energy. It means electrical energy can be produced without doing any mechanical work. That violates the law of conservation of energy. In fact, to satisfy the law of conservation of energy, it is imperative for induced current to flow in such a direction that the magnetic effect produced by the induced current opposes the external magnetic field. In the present case, the relative motion of the magnet with respect to the coil induces EMF in a direction so as to oppose the approach or withdrawal of the magnet. Now let us go back to the example we had considered in the beginning. In this case, the magnet falls very slowly because the copper tube has acquired a changing magnetic field from the falling magnet. This changing magnetic field induces a current in the copper tube. The induced current in the copper tube in turn produces its own magnetic field, which opposes the magnetic field of the magnet falling through it. Hence, the magnet falls very slowly through the copper tube. To summarize, an induced EMF generates a current in such a direction that the induced secondary magnetic field opposes the magnetic field inducing the current. This is known as Lenz's law. To satisfy the law of conservation of energy, it is imperative for induced current to flow in such a direction that the magnetic effect produced by the induced current opposes the external magnetic field. A clamp meter is a device used to measure the RMS value of an alternating current in a current-carrying wire. This device is based on Lenz's law. To know more such applications of Lenz's law, stay tuned.